Good day, students. We spoke about number patterns. This is the third in the series of lectures. The first one we spoke about was number patterns, which we introduced numbers and we showed how number patterns can be used as relationships and we can answer big questions with that. Then we looked at the building blocks of number patterns, which is sequences. And part of the first one was arithmetic sequences. The second part of that we're going to examine is called geometric sequences. And that's the subject of today's lesson. Okay, so we're going to get straight into the subject today. What is a geometric sequence? If I have numbers that look like this, the trick is to try and find what kind of number pattern there is here. So I see 6, 36, 216, so it straight away tells me I should be multiplying by some sort of number, and maybe I can. So let me spread it out and let's have a look. So if I multiply 1 by minus 6, I get minus 6, that looks right. If I multiply minus 6 by minus 6 again, I get positive 36, that looks good, so I'm on the right track. And then 36 by minus 6 again gives me negative 216, so there we go. I can see that I'm multiplying every term by minus 6. So I'm not adding, I am not subtracting. That is arithmetic sequences. I am multiplying or dividing, and that is geometric sequence. That's the main difference between the two types of sequences that we have. Okay, when we test for a geometric sequence, we always look at the second term divided by the first term. So minus 6 divided by 1 is minus 6. 36 divided by minus 6 is minus 6. And if we do that consistently and we get the same answer, then we know it is a geometric sequence. That is the test for it. All right, let's have a look at this word. We say there is a common ratio. Common ratio, what does ratio mean? Ratio means a fraction, and a fraction means multiplication or division. Okay, so that is your clue. When we talk about ratio, we're talking about division, fraction, multiplying. That is geometric sequence. Okay, let's have a look at the definition. If the ratio between consecutive terms, consecutive meaning terms next to each other, is constant, constant meaning they are the same, then the ratio is called a common ratio and the sequence is called a geometric sequence. Okay, that is the definition that we should be very clear about. All right, these words are very important. Whenever I teach these things, I always make sure, please understand the words. When we talk about ratio, ratio means a fraction. It means multiplying or dividing. Consecutive terms again, terms next to each other. Okay? Constant, the same. Common ratio, the same ratio. So we have a geometric sequence. Okay, let's go on. So if I have 2, 4, 6, 8, is that a geometric sequence? So let's have a look. I can multiply by 2, I get 4, so far so good. 6 divided by 4 is 3 over 2. You see, again, I'm using this idea of the second term over the first term, because that is my definition. When I want to test for a geometric definition or an arithmetic, I use the term on the right-hand side, that term divided by that term, that term divided by that term, not the other way around. So 6 divided by 4 is 3 over 2. Not good. 4 divided by 2 is 2. And 8 divided by 6 is 4 over 3. So I've got 3 very different ratios. These are what? Ratios. So you hear that word coming in. All right, so 3 very different ratios, which means that this is not a geometric sequence. Okay, so that's how we test it. In fact, what this is actually an arithmetic sequence, because we're adding 2. 2 plus 2 is 4, plus 2 is 6, plus 2 is 8. So that is a constant addition. So that is an arithmetic sequence. Okay? So I hope you can see the difference between the two. Right. There is the formula for a geometric sequence. We can prove this. It's not very difficult. And I could do that in another lesson. But right now, we shall just go with the fact that this is the formula for a geometric sequence. What does it look like? AN means a term that I'm looking for at whatever position. it's the first term again. The first term is always very important in these sequences, all right? So the first term multiplied by r. R is the common ratio raised to the power n minus 1. So I take r, which is the common ratio, and I raise it to that power. Now this, strangely enough, looks like exponential sequences, which I mentioned in the first lesson about number patterns. We'll come back to that. Okay, let's look at how we can use these things. Suppose you have equipment to enlarge a photo, all right? So you want to take a photo and you want to make it bigger. So you put it on a photocopier machine and it gets bigger. And you take the bigger one and you put it again and it gets even bigger. So you keep doing this and you get a bigger and bigger and bigger photograph, all right? So you want to know, after 5 times of doing this, how big is my photograph? So we want to enlarge it 120%. Okay, we are not adding it 120% each time. We are multiplying it. We're taking it and we're making it that much bigger. So we are talking about a geometric sequence. So we start at 10 and we want to find out after 5 times. So I enlarge this photo 5 times over. How big is that photo going to look? Okay? So I can use the formula for this geometric sequence. And I say you need to find the 6th term. Why? Because the original photograph is the first term. And then I'm going to do this thing 5 times. So I'm going to end up with the 6th position. All right. I can start off by saying the first time I enlarge it, I multiply it by 1.2. That's 20% more. I get 12. I multiply it by 1.2. I get 14.4. And I can keep doing that, okay, till I get to 6. Or, and there's nothing wrong with that. By the way, if they ask you a question like this in an exam and they say, what is the 6th term? You can do that because there's 3 terms. You just multiply the next term by 1.2, 1.2, 1.2, and you've got your 6 terms. They can't tell you that is wrong. That is entirely acceptable. But you can use the formula as well. And just to illustrate, AN, A1, R. So those are our key words. So AN is the 6th term that we are looking for. A1 is going to be the first photograph, which the size of was 10. Okay, the size was 10. R was 120%, so 1.2. And we're looking for the 6th value, so 6 minus 1. And we put that into the equation. Use it on your calculator. Okay, guys, I'm not very mentally sharp to do all these things in my head. All right, use it on the calculator. You get 24.883. And my answer then to the question is, after 5 enlargements of 120%, the photo is going to have a size of about 25 centimeters. So there's a practical application for geometric sequences. Okay, there's another very interesting idea again. Like we had the arithmetic mean, we have what is called a geometric mean. And it is found by finding the positive product of 2 numbers. Now this sounds like a mouthful. You know, normally when you talk to people like this and they say, okay, right, it's time to put the maths book away. Let's take a break because there's too many words here. Okay, let's break it down. What that means is finding the product of 2 numbers. Now that looks so much simpler, right? The square root of the product. Okay, so where would we use that? We can use that to find missing terms in a sequence. How do we do that? Let's look at this. There's a problem again. And you'll notice I use a lot of real-world problems. I don't believe that maths should be in a university, in a dusty PhD, sitting somewhere there, and they're sitting with their books, and they're not contributing to the world. You want to be able to take maths and do something with it. So here there's a problem. A family purchases a home for 150,000. And then 2 years later, the home has a certain value. And if it was increasing geometrically, so now here we're just bringing the maths part of it, how much is the home worth after 1 year? So we want to find out, we know what is in 2 years, we know what it is now, so what is it in between, okay? Now in real life, we have what is called inflation. We have what is called lending rate of interest by the banks. All those things influence the price of our house. If you do financial maths, you would have come across a financial formula to do this. All right, I'm going to come back to that idea. But we can do it using geometric sequences. So if I use this geometric mean, there's another shortcut. I know the initial value of the house was 150,000. I know in 2 years' time, it is 188. So if I multiply that, find the square root of it, I get 168. That is the middle value of the house. So it starts at 150,000. After 1 year, it is 168,000. After 2 years, it's 188,000. Now, I could have done this using financial maths. And this formula should look familiar to you guys. A equals P 1 plus I. So this is accumulated amount, principal amount, I is the interest rate, and N is so many years. So you learn that in financial maths. And that is exactly the same thing as geometric sequences, because this is the term AN, this is the term A, and this is R. Okay? So financial maths actually is derived from geometric sequences. It's not the other way around. So somewhere along the way, people looked at geometric sequences and said, oh, I can use this for finance. Financial maths, there we go. But that is derived from geometric sequences. So again, maths is very connected to life. Okay. And by the way, you could actually then find out that the interest rate was 12%. I'll leave you guys to check that out. You could do that using this formula, or you could do it using the geometric sequence formula. All right, one more thing, connections. Everything we do in maths is connected to something. We never ever do maths in isolation, and that's one of the biggest problems I have with teachers. When you teach maths, it's like, okay, you learn this, then you learn that, and then you learn that, and then you leave school, and then you forget all about it, because you don't need to know it. But if you know that maths is connected to things, then you can use it. Now, when we talk about geometric sequences, I just showed you it's connected to financial maths. It is also connected to what we call exponential graphs. And that whole example that we did with the COVID virus, this is what it's doing. And it's based on information like this that governments all over the world are taking action to do things, starting from simple things like patterns and geometric sequences. Okay? And here you can see the relationship between the graph and the geometric sequence. You can see just the letters are different, but we are doing the same thing. So I can use a sequence, or I can use a graph, the equation, or I can then draw the graph for it as well. So hopefully you see that all these subjects are pretty connected. All right, there's a couple of examples for you to try out. You could try it, and I'll put the answers up. So when you've had a look at it, come back and have a look at the answers. Is this a geometric sequence? Straight away I can say 2 divided by 1 is 2, 6 divided by 2 is 3, so they're not equal. No, it's not a geometric sequence. 1 divided by 2 is a half. Half divided by 1 is a half, so that looks like a geometric sequence. So I can put those down. This one here, 81 divided by 9, minus 9, minus 720 divided by that, minus 9 again. So again, we're seeing that minus 9 is the ratio, and I can work it out. Okay? I know I'm going through that pretty quickly, but the idea, again, is test to see if it's geometric. Take the term after, divide it by the term before. If I do that once or twice and I get the same answer, then it is geometric. Okay. Write an explicit formula for this. We have A1, we have R. And then write the first 5 terms of the sequence, which is the number pattern. If we look at the formula, I want to find out any value. The first value is A1, which is 7. R, which is 1/3 to the n minus 1. So that is your standard formula. I just put those in there. And then if I put the values for n equals 1, this becomes 0. Anything raised to the power 0 is 1, so the first term is 7. The second term, 2 minus 1 is 1, so it's 1 over 3. So 7 times 1 over 3. 3 minus 1 is 2 squared, so it's 1 over 3 squared is 1 over 9, and so on. So I can then simplify this to say 7, 7 over 3, 7 over 9. So here, when you look at this, now you can see a number pattern, isn't it? You can see that the top is 7 right through, and the bottom one is just going. So there is your number pattern coming out of it. All right? Very interesting to look at these things. I hope with these 3 lessons you have a basic understanding of what sequences are. Later on, you will learn about how we add terms in these sequences. That is called series. There's another word for that. So we sum all the terms up, and that will be the next step. Thank you very much. Have a good day.